My name is Greg Freeberry, and for the Evolvable Hardware class, I decided to do my project on adaptable analog filters using PSOQI, which stands for Particle Swarm Optimization with Quantum Infusion. Now, before we can have evolvable hardware, we have to begin with an evolvable hardware platform. This is where the FPAA comes in. The FPAA stands for Field Programmable Analog Array, and it's basically just the analog version of an FPGA, whereas the FPGA has a bunch of logic gates, things like that inside of it, and FPAA has analog components instead. Now the FPAA, like the FPGA, can be programmed and reprogrammed in real time to fit whatever our requirements are. Now a particular topology that I found for an FPAA is this hexagonal topology, and it consists of 7 configurable analog blocks, or cabs, as you can see here, and each cab has 7 connections. Now the exterior ones, 6 of them, all have an input connection, and whereas the interior cell, the interior cab, has no input connections because all its connections are taken up by the exterior cells. But however, each of these cabs all have an output that can be connected to. So basically you instantiate filters on this topology by controlling the transconductances between each of these cabs, which are these connections. Now these transconductances can be set high or low, positive or negative, or 0 if you want them to be turned off. To better illustrate how a filter is made, each individual cab has analog components in it that can be configured to form a first order low pass filter. However, you can also cascade these first order low pass filters together to form higher order filters. And so you could actually instantiate 6 first order low pass filters around the exterior of this topology, or you can connect them all together to get one big 7th order filter. In this particular example, as you can see here, is here's one filter, input 3, and then you take the output from 3 as well, and you get a 2nd order low pass filter. This one right here is just a lossy integrator. It's just a first order low pass filter. This one here is cascaded with these two, and then this one's used as a gyrator, the middle one, to control the gain of the filter. But it's cascaded together to get a 4th order bandpass filter. And you will see more of these because they are my goal filters for the solutions. We'll see more of this later. Now what I used to operate on this hexagonal topology was a particle swarm optimization algorithm. And the basic particle swarm optimization algorithm is just a global swarm algorithm which uses multiple individual particles in parallel to explore the search space for the optimal solution. Now, what that basically means is you have all these tiny little particles, and they're flying around the search space, and each of them represents a solution. And when it finds the best solution, each of these particles tend to move towards that best solution, and they also move towards their own personal best solution. Now, here's a diagram to better illustrate. You have your momentum term, your cognitive term, and your social term. So here's your original position. Here's the final position up here. The momentum term is just whichever way the particle's already moving, plus the cognitive term, which is each particle's own personal best position, its most optimal position, and then the social term, which is the most optimal solution overall, called the G-best, that has been found up to that point. Now this is just the standard basic particle swarm optimization algorithm that we're pretty familiar with. Now QPSO, which stands for Quantum Particle Swarm Optimization, was created by Soon in 2004, and it's based in quantum mechanics. It's probabilistic instead of deterministic, which means that the position and velocity cannot be known simultaneously. So there's no velocity equations in the QPSO. There's only a position update equation. And this is derived from the Schrodinger equation, which governs quantum mechanics. And as you can see at the bottom here, is the position equation that's derived from the Schrodinger equation. Basically you have this P, which is a local attractor, and that's created as you go through the algorithm. And then the M best is the mean best particle, which means you add up all the positions for each dimension of the particle, and then you divide by how many particles you have, and then that will give you the mean best particle. And then U is just a random number. So the only thing that really controls this equation is beta, and that's called the creativity coefficient. So you can raise that or lower that depending on how much effect you want to have the QPSO to have. What PSOQI does is it combines the standard PSO algorithm with the QPSO algorithm. Now the thing about the PSO is that it has very quick convergence speed, but it doesn't have as quality results as the QPSO. The QPSO creates better results, but its convergence speed is a lot slower. So what we do is we start with the standard PSO, we run through all the position velocity updates and all the update equations for the PSO, and then after that's all done, we select one particle to perform QPSO on. This way, we create offspring with the QPSO, and we compare that to the P best and G best of that particle and the G best of the overall algorithm. And if the QPSO generated offspring is better, then we replace it. Otherwise, we just discard it. So this kind of preserves the convergence speed of the PSO while also improving the results using the QPSO.